Ladies and gentlemen, today we are going to discuss the 10 important subjects of electrical safety in low voltage. Please understand that all our programs or the programs which I am making are based out of, or it is applicable for low voltage application, especially within a building or within an industry. Now today it is the 10 points, the 10 important subjects which I feel. See here, some of the subjects which I am going to talk would be more convenient for an electrical engineer to understand, but I am sure more than electrical engineers, there are some engineers from the fire department as well, those who are regularly participating in our program. However, I will try to make it as simple as possible for them to understand. Now, as Mr. Dominic explained, I am a member in the IEC TC64, which is the global committee making electrical safety standards for protection against electric shock and fire. TC81 is the IEC committee for lightning protection. SC37 is for low voltage SPDs. I am also a member in the electrical committee of National Building Code, then National Electrical Code, and so on. But anyway, that is not important now. So I'm going to discuss about the 10 points which has to be considered during the design, erection, and verification of an electrical installation. A short introduction about the company, which Mr. Dominic already told. Actually, during this COVID, as I said earlier, we have conducted a lot of webinars, and then slowly, daily, about 50 to 60 questions come to me on clarifications, and I'm actually a little bit tired of answering. Then I started thinking of some kind of a software which can support the users, and then now we started as a small software called as Solve, but now the interesting point is we are moving towards a kind of an artificial intelligence. We are building up a lot of database into the software so that people can very well log into it and get the answers. We are at 200. We have 200 people working in the company, and we have 2 manufacturing locations. And the subjects which we are always talking is safety. We repeatedly talk on safety. All of you are aware of this. Now, for an electrical installation, I will just hide my video for some time. For an electrical installation, the protective measures required in an electrical installation are categorized into 4. Electric shock protection, protection against thermal effect, protection against overcurrent, protection against over voltage. So basically, protection against electric shock, this is to ensure that the people and the animals are not getting shock. Basically achieved by 2 protective measures called as basic protection and fault protection. This also can be done by an enhanced protective measure. These are a little bit technical words, but for electrical engineers, sometimes these are useful to understand. So basic protection alone cannot provide you safety. You need basic protection and fault protection. Now, these basic and fault protective measures are selected based on the environment where you need safety. For example, some of the protective measures such as automatic disconnection of supply, double or reinforced insulation, electrical separation of one of the item of a current using equipment, or extra low voltage. Actually, these devices, these safety measures, disconnection, double insulation, electrical separation of one of the equipment, and extra low voltage, these are actually the safety measures which can be implemented in general location. That means where common people are available. Whereas in an industrial environment, sometimes you need much more or much different safety situations. And for those environments where you have people, those who are instructed, or people, those who are skilled. So in that area, the safety measures which can be implemented are sometimes called as a non-conducting location, earth-free local equipotential bonding, electrical separation of multiple electrical devices from one power supply. So like that, shock protection it can be achieved by various protective measures. In one building, sometimes you have to implement different protective measures depending upon what kind of application it is, what kind of people are involved, what kind of the devices are involved, and so on. Say, for example, in a hospital, the operation theater is a different environment. In an electronic industry, where manufacturing and movement of a lot of materials are happening, the environment is different. The data center is a different industry. Defense is a different industry. So, like that, each and every application require different protective measures. The second one is thermal effect protection against thermal effect. The thermal effect protection is achieved by avoiding heat accumulation, heat radiation, hot elements, avoiding hot elements in an electrical installation. Then you have to have temperature limits, you have to have seals of cable penetration, and you have to limit the temporary over voltages, you have to limit the lightning surges, and so on. So like that, a combination of protective measures are required for thermal effect. Also, a combination of protective measures are required for overcurrent. Overcurrent, say for example, overcurrent, whenever in the standards or technical books, if it is written as an overcurrent, you should think that it is an overload current or a short circuit current. Both are together called as overcurrent. And then the final one is over voltage protection. Over voltage protective measures against temporary over voltage, sustained over voltage, transient over voltage, harmonics, and so on. All these 4 safety measures are mandatory in an electrical installation. And now these 10 points, which I am going to explain, are basically required to achieve these safety measures. The first one, the fundamental one, is called as system earthing. System earthing, in the sense, most often the electricity is coming from a source, probably a DG or probably a transformer, to a house or to a low voltage electrical installation. System earthing is the subject which deals with how you are getting the electricity from the transformer or from the source up to a consumer's installation, and how you are going to use it safely. System earthings are classified into TN system, TT system, IT system. There are, TN and TT are called as earthed system, IT is called as unearthed system. TN system is further classified into TNC, TNS, TNCS, and a lot of such classifications are there. We were conducting 2 hours session exclusively on system earthing. I'm sure most of you must have already participated in. Now, this subject, it is the first and the fundamental requirement of electrical engineering when it comes to generation, transmission, distribution, and usage of electricity with respect to safety. I would say that every electrical engineer, those who are involved in this field, especially generation, transmission, distribution, and usage, they should be aware of this system earthing. And the distribution companies, they shall apply these safety measures appropriately into their system. As a result, the consumer premise is protected, the animals and other people and animal on the distribution are protected, and so on. Actually, the fundamental safety, as above are told, up to 11 kV supply, 46% or 43% of accidents and deaths are happening at the 11 kV, and probably a large amount in the low voltage electrical distribution. Here, the electricity supply company has got a lot of responsibilities. The safety regulations of the government of India says you should follow a TNS system, means a 5-wire system, or an earthed neutral system, TNCS, 4-wire system. Those are a little bit technical words, but invariably nowadays most of the electrical distribution companies are supplying TT system. And finally, it is actually a kind of a mess. People don't know what is the actual system and how it is working. So actually, the whole confusion of electrical safety starts from the fundamental itself. So the first point which every engineer, those who are involved in safety, they should understand what is system earthing, and they should implement the appropriate protective measure applicable for a certain building or a certain application. This is the point number 1. Point number 2, overload. After every accident nowadays, we say the accident is due to overloading of the circuit. The building is designed 25 years back. Then we have added air conditioner, refrigerator, heater, and so on. As a result, the load has increased. Then the fire or the accident happened. Actually, electrical engineers shall not make this claim, because electrical engineer knows that there are protective measures implemented in a certain installation, and the protective devices are supposed to operate before the electrical installation make a serious accident. So we have a lot of protective devices in our network. Nowadays we have MCCB, MCBs and all, but olden days we have fuses. Of course, fuses are also equally effective if they are appropriately selected and installed. Very important. If we put an overrated device, of course, it may not work. If we put an underrated device, then it may trip unnecessarily. So the challenge here is, the protective devices must be rated appropriately, selected appropriately for that particular application, depending upon the size of the conductors, depending upon the disconnection time, and so on. You can see the selection measures in the standard IS 732 in clause number 4.2 and 4.3. There are different measures to select it. I am not going into detail of those, the entire measures. Basically, these protective devices, such as MCBs, MCCBs, are supposed to protect the wiring. It is not supposed to protect an apparatus. It is supposed to protect the wiring from an overload. That means once when the current is more than the designed current, then of course the device is supposed to trip. So instead of calling an accident due to an overload, we should start calling that the accident is due to non-disconnection of a protective device or non-operation of a protective device. We have to change the term a little bit. Then only if we start calling this as a non-operation of a protective device, then only people will start realizing the seriousness of selecting the appropriate device and put it into the circuit. One of the subject which is very important with respect to overload is the selection of wires. In lot of cases, in last 1 year, I was doing continuously lot of safety audits. Nowadays, almost 4 days I am traveling and conducting lot of safety audits, and in most of the safety audits, the wire selection is really terrible. The MCB, I have a case study. Probably after 2-3 slides, you will be able to understand how it is done. Especially here the issue is, one is the sizing of the conductor. Then the second is copper wires used through or pulled through conduits. Class 5 copper is used, which is having a higher resistance. The third point is too much wires are inside a conduit. If the conduit, let us say, for example, 1-inch conduit, probably you can pull 5 sets of wires, but instead of 5, probably 10 sets of wires are there. The number of wires are very much high, and most of the electrical installations, the shock protective measures are absolutely missing. I have a case study which I will explain to you later. Yeah, some of the terms which with respect to overload, the terms for electrical engineer, whenever we say an overcurrent, we should think that overcurrent is related to overload and short circuit. Overcurrent is related to overload and overload current and short circuit current. Similarly, we call as earth leakage. Earth leakage means there is an insulation failure and insulation degradation in the insulation. As a result, a leakage current is flowing through the exposed and extraneous conductive parts. So here, what you should do is you should have a device, RCD, which is having a tripping current of 30 milliampere is necessary to protect against shock. 300 milliampere is required to protect against fire, and a device of lesser than 500 milliampere, if you have it in your electrical installation, you don't need to test the fault loop impedance. So 3 subjects with respect to earth leakage is there. One is to prevent accident because of an earth leakage, you need to have a RCD or RCCB of 30 milliampere for shock protection, up to 300 milliampere for fire protection, up to 500 milliampere if you wanted to avoid a fault loop impedance test. So this is how you are supposed to do overload protection. Similarly, the third one is called as fault. Actually, short circuit is happening between current carrying conductors, between phase conductors or between phase and neutral conductor. But due to an insulation failure between a current carrying conductor and the earth is called as a fault. It is also called as earth fault. Means a live conductor is in contact with an exposed conductive part. That means the impedance between these two, the resistance between the live conductor and the earth means the body of the equipment is quite less. As a result, a person who is touching probably may get an electrocution, may get a shock. So basically, overcurrent, leakage, and fault are three distinct safety measures. So we should always keep this in mind and select the appropriate protective measure. Case number 3, disconnection time. Very important. A person through his body during a shock hazard, once when the current starts flowing through the body, up to certain time, probably the person is able to withstand. Up to certain time, the equipment is able to withstand without catching fire. So the disconnection time is very important, especially when it comes to fault. As Mr. Apau told, earth fault is the major reason for most of the accidents. For a fault, you can see here what I have shown is this is a transformer. You have a meter, means your point of commencement of supply, your main distribution where I am moving the cursor. Then you have your final distribution board. For final distribution boards, up to 63 amps socket outlets or up to 32 amps fixed electrical installation, the maximum allowed disconnection time is what is shown here: 0.4 seconds in case of TN system, 0.2 seconds in case of TT system. On the same time, the fixed electrical installation, the main distribution boards, the disconnection time is very simple. The tripping time of your MCB, it can go up to 5 seconds in case of TN system and up to 1 second in case of TT system. But please be sure, please keep in mind that these times are derived in the standard, including protective equipotential bonding. Means all the metallic. I have a slide which I will explain later on. So these timings are applicable if you have implemented protective equipotential bonding. If you have not implemented protective equipotential bonding, then the disconnection times, I would say, it has to be even lesser. So the third point is disconnection time of a circuit during a fault. Very, very important. Number 4, earth fault protection. What is earth fault protection? Now I am showing you a TNS network. Means you have a source, you have OCPD stands for MCB, you have a load. The green is nothing but the body of the equipment, and then you have a protective conductor connected back to the neutral of the source. You can find this kind of pictures in all the IS standards. The IS standard I am showing you is the IS 3043. Which is called as the Code of Practice of Earthing, figure number 38. You can find out how to make the earthing and earth fault protection in a DG. Then you see if there is a earth fault, the system shall be designed in such a way that the fault current is quickly returning back to the source. Once when the fault current is quickly returning back to the source, enough fault current flows and it disconnect the protective device. The protective device will be very efficient. If you have more and more fault current, the protective device will be efficient and the disconnection time will be lesser and lesser. So one of the fourth important point is ensure that the fault loop impedance is lesser than the allowed limit and the device is able to trip it. In the upcoming National Electrical Code, we have included this table which says every MCB, you can see MCBs are of type B, type C, type D, depending upon the type of the MCB and its rating. The maximum allowed fault loop impedances are included in a table. Now, the code of practices such as IS 3043, which is not a new code of practice. IS 3043, the first, the first standard came during, I think, 1965 or so. The standard has written very clearly that the fault loop impedance shall be calculated during the design. Fault loop impedance shall be tested during erection and commissioning. Fault loop impedance shall be checked periodically to ensure safety of disconnection of supply. And the first job of the electrical safety auditor is to check this particular parameter. So means you have to have a meter. Nowadays, very good meters are available. You have to have a meter. You have to connect the meter into the circuit and you put it on the test mode. One of our previous webinar was on the testing of this fault loop impedance. We can also send you the link of those videos, which explains how to make this particular test. Now I am trying to explain you one of my experience recently in Kerala. So this particular installation, they had a 500 kVA transformer. The building consists of offices and shops. It's like a semi office come shopping complex. So one of the shop owner, since he was known to me, he called me. Okay, I was also on the way. Then I went there just for a look, and I had the meter. I put the meter into his distribution board and I tested it. It was a 63 amps MCB in a sub distribution board. So the building owner has given an MCB DB to this particular shop, which was a 63 amps MCB. Plus, additionally, there was a 10 amps single pole MCB for some of his light fittings. Now, this gentleman has connected an air conditioner in this 63 amps MCB. He took 4 square mm wire and he has connected to the air conditioner. So I tested that the terminals of the outgoing of this particular MCB. The result which I got is R to P, R phase to earth impedance is 6.52. The fault current is 36 amps. And you can see here the average earth fault current in that MCB was about 35 to 36 amps. Whereas this MCB requires 630 amps to trip within the specific time. So the current which is actually the earth fault current which is flowing is not even, you can see here, this is not even 5% of what is necessary. The current is very, very small. As a result, what can happen is if this air conditioner makes a fault, you can be sure that the result is fire or the result is an accident. The result of this particular study, even if he has got a 6 amps MCB, type C MCB, even a 6 amps MCB cannot trip in this situation. So the installation was so bad. The actual load current was 18 amps, and the phase and neutral he has used 6 millimeter square for the phase and neutral, and for earth wire he has used a 2.5 square mm wire. Why I am showing this is, up to 16 amps. The phase and neutral and the earth, you are supposed to use the same dimension, which is also a violation here. Now, this, from my experience in last 1.5 years, I have tested probably, or not me directly, probably some of my engineers, or we have association with a lot of electrical contractors or the people, those who are regularly attending our trainings. We ask them to buy the meters and they are going to their client place and they are doing the testing, and out of this the results, actually similar result of this shop, it is remaining in hundreds of locations across India. I would say about more than 90 to 92% of our installations, the earth fault protective measures are similar. Means there is no safety at all. It is common in houses, hospitals, and offices. Any insulation failure will result in an accident. Now, in this particular case, the shop owner, he called the building owner. Then we met the owner of this particular shopping complex. But both of them, the owner and the shop owner as well as the building owner, they don't have any idea about electrical engineering. But of course, they are the entrepreneurs. They don't know anything about electrical engineers. They have This building was inaugurated probably just before the COVID. So they had the electrical contractor and there is a gentleman to design the electrical system. Then we started interacting with the electrical contractor. The most interesting point is, I'm so sorry to say that the electrical contractor never heard the name. He doesn't know. The word fault loop impedance itself, he never heard, and he never know that this kind of a test exists. This is the situation. So interestingly, for the first time, this gentleman was hearing the particular name, and I feel that almost 90% of the contractors, it is remaining, the situation is same. And then we get in touch with the designer of that particular building. Interestingly, his situation, he told that no, this cannot happen in my building because I designed the building based on the IS 3043. And then when we asked, okay, did you heard of fault loop or fault loop impedance? He told, no, yes, I did as per IS 3043, but he never heard the name fault loop impedance. And this name is written in the standard in IS 3043, 66 places. This name, its definitions, its application are written. In IS 732, about 62 places, fault loop impedance and disconnection times and disconnection methods are explained. But this is unknown to the user. Of course, he is not an electrical engineer, but unknown to the contractor, unknown to the designer. This is the pathetic situation. So the second part, the electricity supply company. Did the electricity supply company knows it? Neither the electricity supply company nor the electrical inspectorate, they have any kind of guideline to tell every owner that you should do this test. This is missing. Please remember that this test has been included in the IS 732 during 1989. Similarly, we were trying to check the PWD manual because somebody told that this is from PWD. Then we tried checking PWD, CPWD manual. Nowhere these measures are included. So basically, our installations are really in danger. The question which I wanted to ask is, who is responsible and who will correct this? So basically, we are responsible for all the electrical related accidents. Now, the case number 5, protective equipotential bonding. What does it mean is, in every building, all the metallic parts except current carrying conductors or except some communication wires, all metallic parts must be interconnected in such a way that there is no shock hazard. There are rules how to connect and where to connect. Primary protection, supplementary protection, protective bonding, protective earthing, different words are there. But basically, for a non-engineer to understand, very simple, every metallic part in your building must be electrically interconnected except the phase and neutral conductor to avoid shock. Unfortunately, the system which we checked in a hospital, this interconnection called as supplementary equipotential bonding is necessary in a group 2 medical location. Means in an operation theater, shock hazard is more dangerous because the patient, a lot of metallic items are bypassing the skin, resistances are lesser. You need to have a very, very high safety measure. Supplementary equipotential bonding is necessary. Unfortunately, this system is missing in almost 90% of the cases. During the last 2 years, I have visited at least 30 to 32 hospitals for making audits, and 90% cases this is missing. Other cases, of course, we are unable to test. In fact, in the particular hospital which I am referring now, this particular hospital, they have carried out electrical safety audit recently, probably about 6-7 months. They carried out, somebody did an electrical safety audit, and the interesting subject is they have a special apparatus. It's a, I would say, I call this as a black box. They have a special panel, which the supplier told that this is an IoT enabled panel. And this IoT enabled panel the supplier told that it will offer you every kind of safety. And one of the safety feature which they have told me is this particular device the box will send an SMS when there is a fault. That means there is an insulation failure. Immediately the technician will get an SMS, and by the time he get an SMS, he has to go to the panel board and he has to rectify the fault. This is what they think, but this is it is really a pathetic situation. Before you get an SMS, it can catch fire. Before you get an SMS, people can die. So such kind of idiotic boxes are used across India. Then for this particular engineer, of course, fault loop impedance was a little bit unknown. But this engineer or the supervisor, he has worked in Middle East. Then I asked about, have you carried out the RCD test? Because RCD test is quite mandatory in Middle East. Then he told, no, we didn't. Then I asked, okay, have your electrical auditor did the RCD test? No, electrical auditor also didn't do the RCD test. Then my next question is, okay, in that case, what the electrical auditor did? Then he told he recommended a few chemical earthing. So then my final question was, why don't you buy an RCD tester and keep it? Because this is not an expensive thing. You can buy an RCD tester from the market, probably 15 to 20,000 rupees, and you can do the testing. But then his answer was quite interesting. He was saying, this is costly, my management will not approve. And he thought that these tests are not mandatory in India. That means this test is mandatory in Middle East, but not mandatory in India. This is also a truth of our electrical installation. Now, case number 6. Every leakage of current from an electrical installation will see that through the earth means through the metallic parts of a building, there will be a current flow. Ideally, the current flow through the metallic parts must be 0, but due to leakages, there can be a current flow, and this current flow must be limited. Otherwise, it can create a fire. One of the incident, one top leading company, somebody called me that my battery rack is creating spark. What could be the reason? Then very easily we could find out that it was due to a leakage current. They were using a device called as again a black box. I forget the digital earthing system. Means this particular device says that you don't need to earth your electrical apparatus, and that particular system was creating a hell a lot of leakage current, and this was the reason for the arc. So electrical safety, please understand that you don't have any shortcuts. You have to follow the books, you have to follow the science, and only the scientific way of protective measures must be installed or must be followed. Case number 7. Installation category or over voltage category. Here, you must understand that any failure in the insulation of a conductor or an apparatus will create a problem, or it can create an accident. In our electrical installation, starting from the transformer up to the meter board, you have very strong electrical devices which is having a very big insulation. Then at the fixed part of the installation, you have devices which is having a lesser insulation, and your connected devices are having lesser insulation. So there are installation categories, impulse voltages, and so on. What I wanted to tell you is there is a category of device called category 1. Installation category 1 means a sensitive electronic apparatus. You should check the manufacturer's catalog, and if the device is of category 1, actually we are not supposed to connect it directly into a power supply coming from the electricity supply company. From the transformer, a category 1 device we are not supposed to connect directly. But unfortunately, several cases this subject is overruled, nobody bothered. As a result, finally we end up with fire and accident. Case number 8, current loop. Every electrical wiring shall be made in such a way that the current loop, the circulating or the current has to take the shortest path back to the source. If we take a longer path, it may create problems such as electromagnetic interferences, and it can malfunction your electronics. Also, the same case number 8 is a temporary overvoltage, means in case of a fault on a transformer. I'm showing you a transformer here on the left side. There is a fault on the transformer on the HT side. So whenever there is a fault on the HT side of a transformer, equipment in your building can burn. Temporary overvoltages up to 5 seconds can come into your building, which can create a shock hazard, which can create a failure of apparatus. And technically speaking, the shock voltage and the fault voltage must be limited to lesser than certain limit. But unfortunately, this is also a subject which is of new, or which is a new subject for most electrical engineers. Surge protective device, case number 8, protection against transient over voltages. Of course, nowadays this is becoming important because of the suppliers. There are companies, those who are supplying these devices. As a result, this protective measure is getting popular in India. But the previous two, which I told, the current loops and temporary over voltages, are again very minimum. The case number 9 is inspection. The IS 732 or the BS 7671, the wiring rule of Britain, or the National Electrical Code of America, or the NFPA 70, all these standards and the Indian standard IS 732 had included the serial number 1 to 18 inspection points in this standard. This is actually globally it is accepted, and globally this has to be carried out. But unfortunately, this is also missing. The last one is, I would say, the testing of an electrical installation. There are 10 testings. Of course, there is one more, which the foreign countries started doing, which is called as PAT, Portable Appliance Test. This 10 tests plus the one, or at least the 10 tests, are made mandatory in the regulations or made mandatory in the standards. But unfortunately, you have to be careful, and you should do this particular thing. So the case number 10 is testing of the electrical installation, also the periodic testing. In a periodic testing, you don't need to probably do all the tests, but some of the tests are mandatory. So the 10 points which I wanted to force, or which I wanted to see that these are the important points which need to be implemented in electrical installation, is number 1, system earthing; number 2, overload protection and selection of protective conductors and devices; number 3, disconnection time. Depending upon the system, you should implement the disconnection time; fault loop impedance and efficiency of automatic disconnection; protective equipotential bonding; PE conductor current; installation category or over voltage category; temporary over voltages and the EMI current loops; inspection and testing. These are the 10 important points which I felt, if we do it properly, this can actually reduce the number of electrical accidents very much in an electrical installation. Of course, each of this subject, for example, system earthing, that subject itself require 2 or 3 days to understand. We are already conducting webinars. You can also participate in those webinars, but again, this will be exclusive for electrical engineers, because other engineers probably this is a little bit difficult to understand. As I said, each of this subject is important. Now we have made the software solve, but don't think that this is an app which can guide you for an electrical installation. No, this is an app, or this is a software which guide you how to make a safe electrical installation. And most probably, we are actually trying to make it as an artificial AI software which can guide you for investigations. Whenever there is a failure, through some of the simple questions, the software can guide you, or can tell us what exactly has happened. Basically, for safety audits and for guidances, we can use it. So Solve, we have developed a lot of safety measures, and how we are trying to put is Solve will help people in designing the electrical installation. Training modules will be there. Verification of the drawings will be included. compliance to the standards are included, and you will get the support during erection, and all these necessary points are included in the solve, or we are trying to include in the solve. Probably it will take another few more years to finish the software. Only the initial modules for testing and verification is ready. Why I told years is because building up the data is the database is very difficult. We are analyzing each and every failures, and we are putting the data into the system. So now these are the 10 points which I wanted to tell you, and thank you very much for listening to me.